All right, when we talk about vectors in linear algebra, one of the first things we want to explore is the idea of independence. Okay, independence or dependence. We're interested, and we'll start off in the 2 by 2 case because that's easier to visualize and things like that. But all of what we say will apply to larger spaces. Okay, and by the way, when we talk about the two-dimensional space, right, the x and the y that is represented by the xy coordinate system that we're so used to, that is R2. That's what the notation. Three-dimensional space is R3, right? Four-dimensional, obviously, and then sometimes we'll just say, okay, Rn, right? Of course, we can graphically consider R2 and R3, but R4 and Rn are a little bit more difficult. So, but anyway, this is a property. Independence and dependence is a property of vectors, whatever space they're in, however big they are. Okay. So, let's start in R2. And it's a fairly simple idea. Graphically speaking, here's the idea. If you have two vectors, let's draw one, say, here, right? And let me draw another one here. So it's heading in the same direction, but just a little longer. If you, in two-dimensional space, if you have two vectors like that, those two vectors are dependent. Okay, these are two dependent vectors. Okay, they go in the same direction, basically, or they could go in exactly opposite directions, right? So that would also be a dependent vector. Okay, doesn't matter their relative lengths to each other. What matters is they're going in either the same direction or the opposite direction, and we say they're dependent. So it's a very simple graphical idea. On the other hand, if they're not going in the same direction, so if you have one vector that's going like that and another vector that is going like that, those two vectors are independent. Okay. Now, if you can imagine moving this to R3, right? The same principle applies. Deal with a vector in three-dimensional space, and if it's headed out this way to this point, whatever this point is, any vector that heads in that same direction, no matter its length, would be a dependent vector. Okay, but any vector that headed anywhere else would be an independent vector. Okay, so that's what it looks like. But let's stick with the R2 case because it's easiest for us to talk to. So here's so graphically, that's what that means. Basically, if we want to think in terms, because we often need to have some notation to back this up. Okay, we will say this: if vector v is some constant multiplier of u, then u and v are dependent. Now think about that. If v is just u times some multiple, now what happens when you multiply a vector times a scalar? It just makes it longer or shorter or puts it in the exact opposite direction, right? So in other words, if v is equal to some scalar multiple of u, then they are dependent. So that's the notational version of this. Likewise, we could say, so for instance, say this is the vector, well, it looks like it's about the vector 3, 4, right? So we've got the vector 3, 4, and then v is the vector 6, 8. So notice, v is just 2 times u, right? So they're going in the same direction. One's just a stretched version of the other. Or likewise, we could say u is just 1/2 of v. The point is, if I can if I can multiply one vector by a scalar multiple and get the other vector, then they're dependent. Notice I cannot do this over here to these independent vectors, right? I cannot multiply this vector by something to get this, because all you're doing when you multiply by a constant multiplier is changing the length or the direction in the opposite direction. Okay, so that's the idea, and of course that extends in 3 dimensions, right? If I can take one vector, multiply it by some number, and get the second vector, then they are dependent. Now, that's we're moving from fairly simple to work with, but hard to turn into theory and practice, to something that's a little more complicated because it doesn't come with a picture, but it's a little easier to work into our proofs and rules and theorems and analysis. But now we need something that's even a little better. All of these things that give us the same thing, because really the question we have is, if I have 2 vectors or 3 vectors, are they dependent or are they independent, right? Okay, so let me give you the working definition that we're going to use from here on out for determining dependence. Okay, if there is a non-zero solution to a times v, and I'm going to use our notation here, a times u, so it's clear that a is just a number, u is a vector. If there's a non-zero solution to this equation, a times u plus b times v equals 0, then the vectors are independent, are dependent. Okay, all of these mean the same things. This picture, this, and this. But this is the one we're going to work on. If I want to determine if 2 vectors are dependent, I'm going to consider that equation and see if I can solve it. So let's see how that works. R, say u equals 3, negative 2, and w equals, let's do this, 5, negative 7, are they independent? That's the question. So what I want to do is in order to answer that question, I have to solve a times u plus b times w equals 0. Okay, now watch how I do this. Here's a, here is u, so I'm going to write it, we're going to write these as column matrices, right? Column vectors. A times u plus b times this equals 0. We want to solve this, right? So 0 as in the vector 0, right? So you want to solve that. Oh, well, what does that turn into? That just turns into this system. 3a plus 5b equals 0, and minus 2a minus 7b equals 0. So I want to solve that, right? And we have all kinds of ways to solve that. Probably, since this is just a 2x2 system, it's just going to be easy to just do it right by hand. 2 times row 1 plus row 2, replace row 2. Oops, we're going to have to hit a row 2 by a 3. 3 times row 2, replace row 2. 2 times row 1 is 6a plus 10b. I just left them, I'm just leaving it as a system right now, rather than converting it to a matrix, equals 0. 3 times row 2 is negative 6a, that's what we want, minus 21b equals 0. We add those, we get 0. Minus 11b equals 0. Oh, look at that, that tells me b has to equal 0. Well, if b equals 0, I plug that back into either of these two equations and I find out a equals 0. The only solution to this equation is AB, right, is 0, 0. And so since that's the only solution, those two vectors are independent. Okay. If there was some non-zero solution, then they would be dependent. But since 0, 0 is the only solution, then we see that they are independent. Okay, so they are, yes, is the answer to this. Okay, let's check it. Let's check it one more time. R u equal, we use the same u, and this time let's do a different vector. V equals minus 6, 4 independent. Okay, so we'll go through this one more time in order to determine independence. And again, this is for R2, R3, R4. You're going to solve that plus that equals 0. That is this equation, a times 3 minus 2 plus b times minus 6, 4 equals 0, 0. That is 3a minus 6b equals 0, minus 2a plus 4b equals 0. And if I want to go crazy and change this to matrices, it looks like this, right? 3 minus 6 minus 2, 4 times AB equals 0, 0. And so I would like to solve that, and I can do, remember, we can solve it like we did previously, or we can use our good old-fashioned inverse approach. The inverse of A equals, or times B. Let's do that because it's fun. So here's A, this is X, this is B. So what is the inverse of A? Well, 1 over AD minus BC, right? Well, I guess we actually calculate it, right? Since this is a 2 by 2, since A is a 2 by 2, AD is 12 minus minus 2 times minus 6 is 12. Positive 12 minus 12. I can almost stop there, you know, well, carry on, but it looks like we're done, right? Why? Because that's 1 over 0. And who cares what this is? No inverse. And since there's no inverse, no solution. Okay? No non-zero solution, I should say. Well, let's be a little more careful. No single solution. Okay? Therefore, no single solution. Okay, so remember, as a system of equations, there are 3 outcomes. Either you get a single solution, or you have 0 solutions, or you have an infinite number of solutions. Okay, let's walk through this. When there's no inverse, there is no single solution. So we've eliminated that. So we are down to either there are 0 solutions to this system right here, right? Or an infinite number. Okay, now let's think about that. Let's look. Could there be 0 solutions? Well, no. Why? Because 0, 0 is a solution. So there exists at least one solution. So it's not the 0 case, therefore it must be the infinite case. There must be an infinite number of solutions, not just 0, 0, but a bunch of things, right? A bunch of things that are solutions. And remember, we're not even interested in what they are specifically. We just want to know, is there any other solution besides 0, 0? Okay? If there is a non-zero solution, then they are dependent. Well, we've determined there are actually an infinite number of solutions. One of them is 0, 0, but there are an infinite number of non-zero. So U So we found that there were, the only way the way that they would be independent if there was a single solution, and that single solution is 0 0. But we've eliminated that case. Okay. So you can make all kinds of little rules here. You can say things like, for instance, if this matrix, which is the matrix of the two vectors we're interested in, does not have an inverse, then they are dependent. That in fact works for any number of vectors. We did 2 vectors here in R2, we could do 3 vectors in R3. Okay. Now, last, before we leave this problem, we're not surprised these 2 vectors are dependent, because look at them. One of them is 3. Let's do it this way. One of them is 3, -2, right? And the other one is -6, -4. And it doesn't take us long to realize, oh, if I hit this one with a -1/2, I just get this one, right? Or if I hit this one with a -2, I get this one. So in other words, one is a scalar multiple of the other. So they should be dependent.